Okay, so regarding this closed surface, the imaginary closed surface, the radius is r, radius, and let's put the height as this. Okay, so this is the parameter that we will use in order to define the radius, the characteristic of the our closed surface over here. Okay, so let's put this in meter, and this one is also in meter. Okay, now we move on with the Gauss law. S E ds equal to Q E and C epsilon 0. Okay, for this one it's a little bit complicated, so I will start with the left hand side first, and then we will move on to the right hand side of the equation. Okay, so so the left hand side, of the equation, we have E dot ds for a closed surface. So this is equivalent to the surface, the top surface plus the bottom surface plus the bottom side surface. Okay, so here this is individual surface, so we don't need the circle. Okay, so we have to do this one by one. Let me just number this. Okay, for number one, we have here top one, the top surface. So here equal to the, we already know that the electric field is in R direction. Okay, so the ds top, which is this surface area, the normal to that will be in z direction. So ds z. Okay, so here we have it as ds r dot z. So here we have the dot product of two vector which is 90 degree to each other. So this will be equivalent to 0. Okay. Then the same case we'll go with number 2. we have here as e dot d as bottom is equal to this is equal to e yes. So the direction for electric field is r. The direction for the surface is minus z. So this also the dot product between two vector which is 90 degree to each other. So this will be equal to 0 also. And we can move on to the number 3, the last part. Last part here. Okay, so the side one, side surface. So here, so E, D, S. So E is in R direction. So let's see the side surface over here. Okay, 90 degrees to that, as I said earlier, is in R direction. So here we have the dot product between two same vectors. Okay, so this will be equivalent to cos 0. The angle between these two will be 0. So cos 0 is 1. So we are left with E dot S D S. So this is for the side surface. Okay. So the side surface is a cylinder with radius r and height of h. So we can solve this one. The surface area for a cylinder will be 2 pi r h. Okay. Okay, so the total for the left hand side of the Gauss law here for the closed surface which is in the shape of a cylinder is equivalent to 0 plus 0 plus e 2 pi r h. Okay, so later on we can use this and solve the Gauss law we have over here. Okay. Okay, so we come to a blank space whiteboard over here. So from the previous just now, we already know that for the left hand side of this equation, we know that S over here is equivalent to E 2 pi r h. And then we have the right hand side, E and C per epsilon 0. Okay, so now we are going to solve for the right hand side of the equation from here, from this step. Okay, so given that the charge distribution is rho L in the unit coulomb. Okay, rho L in the unit coulomb per meter. Okay, so here to solve this right hand side of the equation, just like the Coulomb's law, we have to make sure that this part of the equation is always in the unit coulomb. Okay, So this part here. So the unit must be in coulomb. Okay. So from what we have over here, we will satisfy this condition over here first. Okay. So here, E to pi RH is equal to Q E and C over epsilon 0. Okay. Okay, so now we are given rho L in the unit coulomb per meter. So in order to have the unit here as coulomb, we must eliminate this per meter over here. So we have to multiply with the height of the charge distribution, which is given by also the height of the our imaginary closed surface. Okay, so from here we can solve the both sides, left hand side and right hand side. So rho L over 2 pi epsilon 0. Okay, we have h in both sides over here, so we can eliminate that. Okay, so in vector, this will be okay. So we already know beforehand that uh, the direction of the electric field is in R direction, as you can see from this figure over here. Okay, so here we just add the direction for that. So in the unit volt per meter. Okay. Okay, so here we can see that the height of the this closed surface is not affecting the electric field at a distance r from the charge distribution. Okay. Okay. Okay, so that we are finished with example 2.7.